Hello everybody. So far we have discussed the conventional machining processes. There are lot of advantages as well as disadvantages in the conventional machining process, but conventional machining process is having some difficulties, specifically if we want to do some kind of non-regular geometric shape. If you want to create, if you want to do machine, if you want to create that kind of different complex geometrical shape, or maybe not very straight channel, maybe if you need to, there is a curved channel is requirement. So, in that case non-conventional and machining process is the most suitable one. So, now we will discuss different non-conventional machining processes, and of course modeling approach, in the sense that our in this case we will try to limit our discussion only to estimate what is the material removal rate, and maybe based on the parametric analysis. So, most of the cases the non-conventional machining process, the modeling approach is becomes complex, and of course it needs very specific treatment if you want to do modeling of particular non-conventional machining process. Rather, in general we can say that there is a limitation of application of the maybe heat transfer equation straightforward, what we have done in case of fusion welding processes. So, we will try to discuss only on the what are the maybe the order of magnitude in the, or what parameter dependency of material removal rate, surface finish, that kind of relative comparison with respect to the different set of parameters, and that we will try to discuss only that point of view. But in general, in non-conventional machining process, first we will look into that principle and mechanism of the different welding processes. Then parametric analysis of heat transfer, material removal, surface finish. Of course, the heat transfer mechanism is very limited in these cases, but other some kind of mechanical analysis is more relevant in case of non-conventional machining process. So, first look into that. So, overall the what are the different types of the non-conventional machining process, and what we can do the modeling things. So, definitely the non-conventional machining process developed because there are certain difficulties, certain problems in case of conventional machining processes. So, we know that machining conventional machining process, there is a generation of the chip formation, and of course it is a, in terms of limitation we can say that large amounts of energy requirement in case of non conventional machining processes. We can expect some kind of unwanted distortion because a large amount of the heat generation, and that heat generation may not be suppressed, sometimes suppressed up to certain extent by using kind of cutting fluid, but not that much extent. So, it unwanted distortion may comes from the high strain rate, and maybe at temperature, some recrystallizations also happen on the surface, maybe generation of the residual stress, formation of the bars, okay. And of course, the mainly limited to create delicate complex geometrics and very fragile on maybe brittle material. Machining of conventional machining process is really very difficult. So, in that sense non-conventional machining process is advantageous. But in what perspective different non-conventional machining process has been developed? First we look into that is workpiece hardness is very high, for example very high strength, very high having material having very high hardness above 400 HB. In that cases there is a difficulty of application of the conventional machining process. So, in that sense the non-conventional is more suitable, and of course, if workpiece is too soft or too flexible, that it may not sustain with the application of the cutting process or grinding process. So, in this case this type of difficulties may be possible to overcome in case of non-conventional. Of course, we already mentioned that very complex shapes such as internal and external profile, or maybe very small diameter holes if you want to create. So, then non-conventional machining process is the most suitable one. Surface finish, tolerance, and of course, if we want to do kind of different finishing operation if you want to. So, non-conventional process is more suitable. Then temperature rise and residual stress, definitely in these cases the temperature rise is very limited in case of non-conventional machining, and that is the main difference. And of course, there is a temperature rise and microstructural changes is rarely in that cases. So, residual stress generation in the machine component using non-conventional machining process is very limited. So, in that sense it is very much advantageous as compared to the conventional machining process. Non-conventional machining refers to a group of processes that removes the excess material by using, if you look in different techniques involving some mechanical energy, application of the thermal energy, application of the chemical energy, or application of the electrical or electrochemical energy. But the main difference is from conventional machining process, it is not requirement of any kind of very sharp cutting tool what we use in case of conventional machining process. And of course, in general the rate of the material removal is very less in case of non-conventional machining process as compared to the conventional processes, because the non-conventional machining process the main focus is to achieve the to desire different types of the material, maybe very difficult to machine material, for example very brittle material, glass, that kind of material, or if you want to achieve very good surface profile, very good finish. So, in that sense the material removal rate is impractical, rather the other aspect is more practical in that case. So, that is why we focus only on the non-conventional machining process, where there is a requirement of the very fine hole, for example very good surface finish and very complicated shape, which is not possible using the conventional machining process. So, now we look into that what are the different machining methods. Traditional machining methods, we know there are several traditional, for example turning, shaping, planing, milling, drilling, grinding, these are the traditional machining processes that we have already discussed. But if you look into that non-conventional processes, where which is different from the conventional processes, where we can use the simply mechanical energy to develop the process. For example, abrasive jet machining, ultrasonic machining, abrasive water jet machining, and these are the apart from that even there are other types of the non-conventional machining process has been developed by using some kind of mechanical energy. Or if you look into the thermoelectric energy, so there is a non-conventional process, the electrode discharge machining, EDM, then electron beam machining, then laser beam machining. These are the typical thermoelectric energy is converted to used, basically utilized for the machining purpose. And then electrochemical or chemical energy source can be used for machining purposes, for example electrochemical machining and only chemical machining. So, all principles we will try to discuss one by one. But apart from that, if of course the main difference traditional non-conventional machining process is that non-conventional we can achieve very good surface finish and desirable characteristics is possible to achieve, which may not possible to using the traditional. But if we combine these two, probably we can achieve increasing the metal removal rate, as well as the what are the difficulties in conventional process that can also be achieved by using the hybrid processes. For example, electrochemical sparks machining, and this hybrid process electrochemical grinding. So, it is a grinding process and maybe merge with the electrochemical machining principle, and then we can achieve advantages of both from traditional welding process, traditional machining process, as well as from non-conventional machining process. Similarly, electrochemical electro discharge grinding also possible, and electrolytic in process dressing, ELID, that kind of different type of the hybrid process, and many more hybrid processes has been developed by using merging the concept of the conventional machining process as well as the non-conventional machining process. So, we will try to look into what are the principles, type of energy sources, and what are the different medium are used for different process. We can get the idea of these things, the type of energy, what are the main processes, energy sources, tools, required transfer media and mechanism of material removal. In overall we will look into that. First, if we look into that mechanical energy, if you assisted non-conventional processes. So, these are the very common processes we use, that ultrasonic machining USM, abrasive jet machining, water jet machining, abrasive water jet machining. Definitely ultrasonic machining energy sources are ultrasonic vibration. So, tool is the sonotrode, and then between the tool and the workpiece there is a passage of the abrasive slurry. So, that abrasive particles basically try to erode or creates the abrasion to the workpiece as well as the tool material. So, here transfer media is the abrasive slurry, and because that is in contact with the workpiece and the tool material, and mechanism of material removal we can say the erosion or abrasion. Similarly, abrasive jet machining also. So, there is a creation of the pneumatic pressure. So, pneumatic pressure creates the jet of the abrasive particles along with some kind of carrier gas, and then abrasive jet impact on the workpiece, and then that creates kind of erosion to the workpiece surface. So, transfer media in this cases is air. Similarly, water jet machining, we just simply create a jet of water, and that normally removes the material, and of course, the tool is the water jet directly used as a tool to the workpiece for the cutting purpose or removing the material, and of course, in this cases some sort of hydraulic pressure is required to create the jet. Similarly, combining principle of the abrasive jet machining and water jet machining, that is abrasive water jet machining. So, here taking the advantage of both water jet as well as the abrasive machining, and then it creates the abrasive water jet transfer media you can consider as a air, and of course, then erosion or abrasion is the main mechanism to remove the material. So, apart from mechanical energy, there may be the possibility of the chemical energy can be used in non-conventional machining process. For example, CHM chemical machining, here we can use the kind of energy source, we can use the kind of corrosive agent. So, transfer media some kind of etchant or reactive environment. So, that will remove the material by the reaction, and mechanism of the chemical dissolution or ablative relation is the main mechanism, such that during the chemical reaction it removes the material. So, definitely in these cases the thin layer of material removal is possible. We cannot compare the removal of the material as compared to just simply turning process in conventional machining process. So, here the rate of the material removal rate is very low in this case, and of course, electrochemical machining process, in this case high current is processed, and then through the there is a tool material we can use as the electrode, and transfer media, the electrode is in contact with the workpiece through the electrolyte. Different types of the electrolyte we can use depending upon what type of material there is a need of the removal of the material. So, it is a simply electrochemical machining is a kind of opposite action of the electroplating, where we can just remove, we can deposit a layer on the surface, but in this in machining process we just remove the layer by controlling the choosing of the electrolyte, and of course, the choosing the different polarity of the electrode on the workpiece based on that, and of course, the mechanism is the anode dissolution rather than deposition. Here is the anode dissolution through ion displacement, that means anode, that means workpiece is reaction happen, workpiece is basically dissolution of the workpiece normally happens in this case, and electrolyte with the high pressure, this carry the dissolution part of the workpiece. This is the electrochemical machining. Apart from that, thermal energy can be directly used for the different machining, non-conventional machining process, such as electrode discharge machining, so high voltage, electro beam, ion beam machining, laser beam machining, as well as the plasma arc machining. So, if you see electrode discharge machining, high voltage, and there is a create the spark between electrode, but in this case the spark and that transfer media means that is merged the contact between the electrode or workpiece through the some kind of the dielectric fluid. So, first melting and vaporization is the main mechanism. First melt or vaporize the that part, directly vaporize the part by the application of the thermal energy. So, that is the principle of the electrode discharge machining. Then similarly, ionized material energy source in case of electron beam machining, Here under the vacuum we create the electron beam, and that simply melting and vaporizing a particular very localized zone. Similarly, ion beam machining, laser beam machining, the different thermal energy sources are used, and tools, all these cases, for example, electron beam directly used to remove the material. In case of ion beam machining, ion beam is responsible to remove the material. In case of laser, the laser energy or laser beam directly used. In case of plasma machining, basically plasma jet is used to remove the material. So, but all these mechanism are based on the melting and vaporization of the substrate material. So, these are the basic classification of the different types of the non-conventional machining process. Of course, there is a lot of machining non-conventional machining process has been developed, but these are the main non-conventional machining process that we are supposed to discuss here. What is the need requirement of the non-conventional machining processes? Definitely, its one advantage is a tool not necessarily be harder than that of the workpiece material. That is the main advantage, and that means sometimes the non-conventional machining process has been developed independent of the hardness of the tool. And if we compare with respect to the conventional machining processes, definitely the hardness of the tool must be greater than that of the workpiece material, but in case of non-conventional, that limitation can be overcome. Small size non-circular holes can easily be produced by non-conventional machining process. So, if there is a requirement of non-circular hole, then non-conventional machining process is the best suitable in that case. Machining of the very brittle material, very fragile material using traditional process is really very difficult. For example, machining brass, ceramics, carbides using conventional machining process is really very difficult. So, in that case there is a need of kind of non-conventional machining process. Of course, at the same time it's a metal becomes very soft. For example, rubber, it's very difficult to doing the machining operation using conventional processes. So, in that case non-conventional is the one of the most suitable method for the machining of the rubber, and of course non-conventional machining process can produce much more complex concave kind of shapes easily be produced using non-conventional machining process. So, there is a need all these cases we point out that we can find out the application of the non-conventional processes when there is a having certain limitation of the conventional processes. First we start with the mechanical based processes, ultrasonic machining, water jet machining, abrasive jet machining and abrasive water jet machining, and all these processes will try to look into modeling approach in the sense that we will try to do some kind of estimation of the material removal rate and to some extent surface finish, and all these cases the parametric approach is more suitable in case of non-conventional processes, because the influence of the different parameters is really highly nonlinear in that sense. So, most of the cases if we know the parametric approach means what is the role of individual role of the parameters to the process, and we will try to correlate kind of statistical relation, and if we assume by assuming certain relation in terms of geometric curve, and then we find out what is the coefficients of this relation. For example, if we do find out say as following certain relation between the material removal rate and the different between the different parameters of a process. So, we find out if we assume some kind of polynomial function, then we need to try to find out what are the different coefficients of the polynomial by comparing the by simply fitting this curve with this experimental data. And we regression analysis can be followed in these cases. So, apart from doing the conventional way to find out how the modeling of the non-conventional machining process, the other approach simply statistical modeling approach is more popular in case of non-conventional machining process, but till we will try to look into very basics things what way we can model. Model means here in the sense that we try to estimate what are the mainly the material removal rate for the different non-conventional machining processes. First start with the ultrasonic machining process. So, definite ultrasonic machining process we can use the very hard and brittle material, specifically for hard and brittle material. So, easily chipping or rupture of the materials may happens and we remove the material, but how it happens? Simply oscillating tool in the ultrasonic frequency, maybe 18 to 20 kilohertz, and with the amplitude of the 10 to 40 micrometers. So, by application of the electrical energy we can utilize the vibratory energy here, and then create the mechanical vibration, and then vibratory energy is responsible for the removal of the material by creating that kind of in the range of the parameter range, in that 10 to 40 micrometer is the ampere, and 18 to 20 kilohertz is the frequency. So, it is simply the abrasive particles with this vibration. Abrasive particles is a hammer, basically impact on workpiece material as well as the tool material. So, there is a wear of the tool also happens in this process, and but the vibration is actually transmitted to the abrasive slurry via tool. So, tool actually transmitted the vibration energy to the abrasive slurry, and then from the abrasive slurry then impact on the workpiece. This way it transfer the vibration energy to remove the material. Here you can see the diagram, a schematic diagram of this ultrasonic machining process. So, see there is a transducer also there here. So, transducer is basically converting the electrical energy to the create the vibration, and we can use this. This is the tool material, and here you can see that tool material, this is the workpiece material. So, between the tool and workpiece there is an abrasive slurry filled with this thing. So, tool is not in directly contact with the workpiece, rather tool is contact with the abrasive particles, and then abrasive particles are in contact with the workpiece. But in this case what we transmits the vibratory energy to the tool, that is a that we use some kind of the concentrator can be used, and of course, in this case the other system, it is part of the cooling water in and cooling water system we use, and definitely the transducer is mainly the this part that creates the vibration from the electrical energy, and frequency around 20 kilohertz, amplitude may be 15 to 20 micrometer, or it can be range up to 40 micrometer to discuss this thing. Now, what are the typical characteristics of this ultrasonic tool? Tool material not necessary in this case is very hard, but to minimize the tool wear, the constructed it's constructed of the relatively ductile material. So, it helps, although there must be some amount of the tool wear during these things, but if it very brittle material, the material removal may be very high, rather if you use the ductile material. So, not exactly the material removes by directly the rupture of the material, rather high plastic deformation may happen in case of ductile material. So, that is why it reduces the amount of the wear if you use the ductile material. So, tool should be ductile material in ultrasonic machining process. Commonly used material, brass can be used, mild steel, stainless steel are normally used as a tool material, but harder the tool material, faster the tool wear rate. So, that is the main thing in this process, that we should not use very hard tool in case of ultrasonic machining process. Then what is the role of the abrasives? Abrasives should be harder than the material, because abrasives are actually in contact with the workpiece. So, abrasives should be harder than that of the workpiece material. So, then abrasives are cutting zone, and then washed either worn abrasives and from the cutting zone. So, worn abrasive the dual role. First is the abrasive impact, remove the materials at the same time, once chipping the material, and then workpiece material along with the abrasive washed away from the workpiece surface. So, of course, certain cases if there is a flow of the abrasive slurry, that material removal due to the cavitation effect may or sometimes is active, and that normally happens during the return stroke of the tool. Now, if you look into the modeling part of abrasive machining process, so we assume that mechanical abrasion occurs due to the direct hammering of the abrasive particles to the workpiece. What are the assumptions? So, in this case definitely the material removal rate is depends on the what way the particle impact on the workpiece, and what is the amount of the volume of from the workpiece is removed per particle from single particle. So, that is why volume of the work material per impact is the material removal depends on these things. Then if we look into the material removal in terms of the other parameters, so definitely it is a number of abrasive particles per cycle. So, what are the now if we count is what is the material removal for one particle, then we count what is the number of particles per unit cycle time, then we count per unit time what is the number of cycles. So, that is why all material the removal rate depends on these three parameters. Now, finally, we can say the volumetric in terms of the volumetric material is MRR is the material removal rate, volumetric material removal rate is basically equal to the volume impact, the number of particles, and finally what is the frequency. Sorry, N is the number of abrasive particles per cycle, and F is the frequency, that means cycles per second. That means finally it represents what is the amount of the volume is removed per unit time. So, that represents the volumetric material removal rate. If you multiply with the density, then it becomes material removal rate, but that in units should be mass per unit time. Now, what we model it, what are these things? First is we assume the indentation caused by a impact of a rigid spherical particles of diameter d on the workpiece surface. For example, this is the workpiece surface and some spherical particle impact on this thing. Diameter of the spherical particle is small d, and of course, diameter of the indentation is basically capital D. And we assume that it creates kind of depth equal to small h. So, in terms of h or d, capital D and d by 2, we can say this is basically d by 2. Now, from this triangle, say O, A and B. So, triangle O, A, B, we can find out that d by small d by 2 square equal to capital D by 2 square plus small d by 2 minus this OA, basically small d by 2 minus h square. So, once we do this, and we can find out that d by this expression capital D square equal to 4 dh minus 4 h square. You can find out that things, if h less than d, then maybe we can neglect this part, and then finally we can estimate d equal to 4 d square equal to 4 dh, and we can find out the capital D equal to twice, approximately twice root dh. So, then volumetric rate, volumetric material removal rate, which is represented by small v, that means per impact of the one particle what is the amount of the volume is removed, and then n is the number of particles impacting per cycle, and then multiply by f, what is the cycles per second. So, I can say if L is the dimension, the volume per time, this represents the volumetric material removal rate, what is the total volume per unit time removes. Now, once V and F, so V can be represented like that, V equal to small v, the volume of the material that is removed per impact. So, this it creates this kind of profile. So, we can consider this as a hemisphere, half of the sphere having the diameter capital D. So, then what is the volume? Half of, so half of the sphere volume 4 by 3 d by 2 is the radial, this is the volume. So, this corresponds to the half of 4 by 3 by 8. So, 1 by 6 by d cube. So, this represents the per impact with one particle, what is the amount of actually volume removed from the workpiece surface. So, we put this is the V amount, this is N, this is F. Now, we replace D in terms of H, because H is the depth. So, H if we put in terms of capital D and H. So, D if we put this D here, then it becomes twice by third by dH 3 by 2 N F. So, this is the estimation of the volumetric material removal rate, And of course, in this case the particle, this if you see it is in terms of d, h, n and f, because d is the diameter of the particle which can be measurable quantity, which can be measured. H is the, we can measure up to the what is the depth is increases per impact, H can also be measured, and then n is the number of particles per cycles can be measured, the n is it is known, and f is the frequency cycles per second. So, if all parameters are known to us, then we can easily estimate what is the approximate volume flow rate, but of course, in these cases we assumes that it creates exactly the it is impacting only on the spherical particle, but practically may not be the very spherical particle, this can be kind of irregular shape. And second one is that when it is impacting on the workpiece surface, it also creates material removal, which we assume the it creates the geometric shape of a sphere having the diameter d, which is basically indentation, diameter indentation. That assumptions may also not correct in practical application, but roughly you can estimate if you know all these parameters. With these assumptions, assuming the spherical particles, then we can estimate what is the material removal rate in this case. Of course, we can estimate other parameters also in ultrasonic machining process. So, mean speed of the tool, actually the feed rate of the tool, mean speed of the tool is very low. Therefore, mean static force can be estimated. For example, normally if we estimate the force F axis, how it varies with respect to time t, and of course, it is a this is the time axis, but I say that is the one cycle time capital T, and most of the it's normally found out that this variation of the force with the during this process normally you can find out such that this becomes corresponds to the F I maximum force at this point, and this variation normally happens over a small time. I think we can say that it is a delta t time. There is a over a delta t time, there is a rise of the force can create goes the maximum when it try to impact, and of course, therefore, mean static force applied on the tool must be equal to the mean force of the tool applied on the grains. So, maximum impact force, if we assume this F I max, and that of course, the maximum force raise over a small period of time delta t, and then we can find out maybe average value which is in between, it is a which average value, but over a cycle time t. So, say I think it is say average value is the f, or I can say that sorry f, suppose this is f, average time is f. Now, what is the amount of the this thing Fs impact during the impact delta t maximum below impact force is given. So, Fs can be integrated, what is the force which can be integrated the over the cycle time, that this thing which can be actually be represented by this such that Fs into t, t is the over the cycle time, which is equivalent to this total area, which corresponds to this, making the averaging, it should be equal to integration of f I as a function of t into dt. So, that makes the average, and from here we can find out the what is the average force. From here you can estimate the average force here F s equal to this, which is corresponds represent this area, sorry it represent this value F s, but we making simply area balance, and we can find out what is the force can be estimated from that. Now, if we assume this is the, if we, but if we want to integrate this thing, we know the, we should know what is the actual shape of the curve. But if we assume approximation that it is a shape is triangular, then we can make the assumptions that is the say F s approximately this. So, in these cases the average force into that total cycle time t, which is averaging over the total cycle time. Average force is simply representation of this over the cycle time, the constant force exists, that we can say this is the average force, which is equal to the this if this is as a triangle. So, what is the area of this triangle? Half of delta t into f I max area okay area delta t max. So, from here we can find out f s equal to f I max into delta t divided by 2 t. From here we can find out this is the average force, what is the time period over the cycle. So, this way we can estimate the average spin, because the impact all these things is really very random in nature. So, it is rather to look into that what is the maximum force it can achieve, and based on that what is the average we can estimate during the impacting in ultrasonic machining processes. But apart from these things, so once we show that this impacting on the particle is impacting on the tool, but at the same this particle is in contact with the tool material. So, there may be some depth of penetration also happens to the tool material, because tool is in contact with the workpiece particle, and then particle again in contact with the workpiece. So, if we assume that this indentation is happening, total indentation can be due to the workpiece and can be due to the tool material, that indicates the total indentation during the when one particle is impacting on the surface in ultrasonic machining process. So, this simple calculation we can do if we know the one parameters, and then we can estimate all these things. Few parameters if we know, we can estimate these things. For example, we can estimate this average force by the tool. In this case, if we know the what is the delta t, basically what is the delta t over which there is a rise of the force from 0 to exactly the maximum, and what is the maximum amount of this thing, if we know the cycle time and all this known to us, then we can estimate what is the average force acting during this process. Now, during the period delta t, n is the number of particles are actually simultaneously in contact with the workpiece, and definitely the f I max is achieved with the application of the simultaneously several n number of particles. And of course, if we know what is the number of abrasive particles are actually in contact with the workpiece, then per abrasive particle the force can be divided this thing. So, per abrasive particles the calculation of the force is maximum force divided by number of particles. This is the maximum amount of the force can be exerted by single particle. Approximate area of contact per abrasive grain on the workpiece surface. So, if we see the abrasive the indentation diameter is equal to d actually. Indentation diameter by the tool is actually d. So, such that the area of on this side projected area is a pi by 4 d square, and then pi by 4 d square, and we know that d is also equal to twice root over h into small d. So, from here we can estimate the pi by 4 d square equal to pi by 4 into 4 h d. So, that corresponds to pi d h. This is the projected area over which the force is acting. So, that maximum stress developed in the workpiece per single particle, we can say this is the force per particle, maximum force can goes up to this divided by the cross sectional area. Cross sectional area can be estimated that pi d h w. So, that represents the maximum stress can be developed in the workpiece material. So, definitely we should know all these values n, f I max, and what is the particle size d, and what is the indentation goes to the workpiece. All these parameters known to us, then we can estimate what is the maximum stress developed in the workpiece. This way it can be calculated. Now, if we look into that, ultrasonic machining overall, what are the advantages? It is the safest all machining process, and there is no cutting, no voltage, burning, chemical reaction does not happen, or dangerous mechanical motions not involved in the ultrasonic machining. So, this way it is a very safe process. No effect on the material structure, because the temperature rise is very minimum in these cases, and different type of the shape application, hole drilling of the any shape, blanking, 2D profile cutting, depending parting of piercing of the dies, all this kind of application we possible using the ultrasonic machining process. But disadvantage, material removal rate is very low. So, that is a general disadvantage in is most of the non-conventional machining process. Tool wear, because we normally use a duct tool is made of ductile material. So, there must be some amount of the tool wear, that is the one serious problem in case of ultrasonic machining process. If it is a very soft material, then its ultrasonic machining process is not suitable, maybe other non-conventional machining is more suitable. Small aspect ratio 2.5 accurate hole can be used if we cannot excel much more precision or aspect ratio to achieve using ultrasonic machining process. Poor machining accuracy is little bit less as compared to the other process due to lateral vibration in these cases. So, lateral vibration is also important. So, that it depends on the what amount of the lateral magnitude we are giving. There may be the sticking of the abrasive particles may possible, and that may require some cleaning operation. So, of course, it depends on the what is the size of the abrasive particle and distribution of the particles in a sample. So, all this kind of disadvantage normally exist in case of ultrasonic machining process. Now, we come to that point, water jet machining. In water jet machining, the key element is the water jet. So, as simple as that create a jet of water that travels can be Mach 3 or around 900 meter per second is possible to achieve. So, when the stream strikes the workpiece surface, its erosive force of water removes the material rapidly. That is the main mechanism water jet machining. But kinetic, the principle, if you see the kinetic energy of the high velocity and high pressure water jet coming out from the nozzle, and that can utilize for the cutting purposes for a particular material. So, most of the kinetic energy of the water jet is basically converted to the high pressure energy, and that called the stagnation pressure, when it is impacting on the workpiece surface. Schematically, you can see that accumulator check valves also there, and then there is a two motor and pump. So, one is the oil pump is basically hydraulic oil to create the pressure, high pressure, and of course, water in, and we can use some filter such that we create the very filter water we can use, and we can intensify, just increase the pressure of the water. And accumulator is also necessary in this case, probably in this case to supply continuously smooth high pressure water. That is why it accumulates, accumulator is requirement. Water transmission line and controlling valve, on off valve we can use, and from the head and then directly impact the workpiece surface. So, schematically it is very looks very simple diagram in case of water jet machining, but it involves a lot of parameters to control to get this successfully utilize this process. What are the equipment are, say, pumping unit, cutting unit, the catcher unit. So, pumping unit just to pump the oil, to pressurize the oil, and these things, that is the heart of the is just to pressurize the oil. And electric motor, heart of the unit to drive, basically motors drive the oil pump, and then oil pump to pressure the oil, then intensifier acts as a high pressure pump using the low pressure, generate the high pressure water, basically intensifier creates the high pressure, generate the high pressure water, and accumulator storage of the high pressure water to avoid the pulsation. That means, when we supply the water, it should not be interrupted, or to avoid any kind of pulsation, the accumulator is used. Then cutting unit, simply use the nozzle from the nozzle that creates the high velocity jet of water, and then catcher unit basically it suppress the very high noise and minimize the exposed length of the water jet for the safety purposes. So, catcher is used mainly the safety purposes. Basically, what will happen after impact the high jet on the workpiece, and then catcher is used to not to spread this water and for the safety purpose. Mechanism of removal is simply erosions is initiated and by formation of the micro and macro crack, and then further development of the cracks occurs once due to the propagation of the stress wave and by repetitive impact of the water droplet. So, water droplet, this is the typical mechanism, propagation of the stress waves, but there is a requirement to initiate the formation of the micro crack first. Extend and enlarge the crack, and the material removal occurs due to the fatigue, after a certain number of cycles. When equivalent dynamic stress basically generated by the water jet exceeds the endurance limit of a particular material. So, in this case the material removal leg by the mechanism of the fatigue. So, just by application of the repeated loading to a particular surface, once this covers the endurance limit of a target material, then it removes the metal. So, that is the mechanism of a water jet machining process. Now, if you look into different parameters of the water jet machining process and what are the influence on that, we can see that increase in water pressure, definitely if we increase the water pressure, jet pressure will increase and it will jet flow will increase, and basically it increases the cutting capability. Depth increases can also be imposed by using the water pressure from both metals and non-metals. So, if you increase the water pressure, so definitely the depth of machining also increases, and of course, there exists some kind of threshold pressure above which it will remove the material from the workpiece surface. Cutting ability will be maximum if it is focused on the normal to the workpiece surface, and of course, depth of groove, that means depth of groove basically decreases if we increase the stand off distance, that means between the nozzle exit and workpiece material. So, stand off distance is very important parameter that actually influence on the material removal rate. At the same time, it also influences the precision of the geometric shape to produce by any kind of by this kind of water jet. So, material removal rate also decreases due to the reduction of the, if stand off distance increases when the jet importing only on the workpiece surface, in that cases the velocity will decrease if stand off distance actually increases. So, definitely stand off distance, accuracy and the quality of the cut it depends. So, some optimum value of the stand off distance is required, and a metal removal rate also increases with increase in the nozzle diameter, but we can increase the too much of nozzle diameter, then at the same times there may be the the surface quality may also affect. So, all these parameters need to optimize by looking into the parametric analysis or just what is the impact of the parameter at the on the material removal rate or the accuracy to produce for a particular process. Application, water jet machining is simply used for soft material mostly and provides the unidirectional cutting at very high speed, clean and sharp cut is possible, no tool wear, no tool never dulls or breaks may be involved. For example, ultrasonic machining basically there is a concern of the tool wear, but in these cases we can find out no tool wear. Dustless environments is required sometimes, that is why is the in certain cases specifically cutting of the fiberglass. No heat generation, no thermal degradation of the workpiece material property. So, that is why it is very much advantageous for now unwanted distortion, residual strength not be there. Limitation, it is a very expensive equipment, maybe higher safety consideration is required due to the high pressure, noise and high pressure to handle, because sometimes it cross the Mach number also. So, noise and pressure is very important. So, the safety concern may be required in these cases. Contaminated water must be treated before disposal. So, contaminated because water may contaminated during this process. So, it can be water must be treated before use it. Brittle materials, this is the common problem, brittle materials may crack by using the water jet machining process, the because if we look into the mechanism for that, it is basically removes by the fatigue action and for a particular material using water jet machining process. So, fatigue action may not difficult, action may not be proper, it creates kind of crack in case of specific for the brittle material. Abrasive jet, now we will start with the abrasive jet machining. This is another non-conventional machining process. In abrasive jet machining, a focus stream, high velocity stream is used, but that stream along with the gas or any medium, gaseous medium normally used, we mixed with the abrasive particles and then create the jet, and that will impact on the surface and removes the material. So, using some kind of carrier gas is required that actually hold the abrasive particles and can create kind of jet. So, brittle fracture it normally happens and the carrier gas carries the, once the brittle fracture happens, the carrier gas also helps to carry the dislodged small workpiece particles with these things. So, this process is very much suitable for brittle material and fragile material abrasive jet machining, but abrasive jet machining is differs from the sand blasting processes in the aspects of the particle size, abrasive particle size, and of course, what we can control the different parameters, action process parameters. In that way, it is different from the blast process, conventional sand blasting process. So, here we can see the abrasive jet machining unit is simply vibratory source. Here the mixing chamber, the carrier gas and the abrasive particles are mixed and then processed through the creating the gas supply, and filter regulator also there. Here regulator regulates the gas supply, and once it creates, then it creates the high pressure gas, passes through the nozzle, and nozzle actually creates the jet, and jet will directly impact on the workpiece. So, instead of simply water jet machining, instead of water, here you can use the carrier gas, but that carrier gas carry the abrasive particles. Elements: gas propulsion system, metering system and delivery system, these are the three basic elements. So, gas propulsion system, so steady supply of the clean and dry gas used to propel the abrasive particles, so that to propel the abrasive particles, and proper filters to avoid the water or oil contamination or abrasive particles is also required. Commonly used carrier gas is the nitrogen, simply use the air, apart from the nitrogen can be used, carbon dioxide can also be used, but oxygen must be avoided because it because of the fire hazards. Mixing system, that adjustable abrasive particles into gas stream, this is the powder hopper that feeds from the powder abrasive particles into the vibratory chamber, that actually in vibratory chamber the abrasive particles are mixed with the jet, mixed with the carrier gas, and then that creates the uniform jet. From that point it creates the uniform jet. Delivery system, it creates consists of the nozzles and maybe mask and some abrasives at the delivery system, and then nozzles is simply the contact with the abrasive particles, and that moving at the very high, it creates the high velocity jet by using the nozzles. Mask, the role of the mask to protect the unwanted overspray, to if you want to don't create kind of large holes, it is an intricate shape. If you want to produce, we can create the mask, and that according to the marks the shape can be created, and of course control all this thing without the nozzle and the tracing of the shape. So, not only controlling the tracing of the nozzle and size of the nozzle and tracing of the sizing of the nozzle and tracing of the shape, apart from by using the additional features by introducing the mask, we can control the different intricate shape also using this process. And of course, once done, abrasive collecting system also there, and this maintain the operator's exposure to dust within the permissible limit, that we simply collect the abrasive system. So, abrasive jet machining, mechanism of material removal in abrasive jet machining. The ductile materials is a plastic, definitely ductile material, plastic deformation will occur, or maybe cutting action, cutting wear, plastic strain and deformation wear is the main mechanism for abrasive jet machining. For brittle materials, simply rupture or elastoplastic deformation, and using the critical plastic theory, radial cracking and propagation, surface energy criteria, all criteria can be put to decide the or analyze the mechanism of the material removal in abrasive jet machining, but this which is beyond our scope. Applications: abrasive particles, assumptions, basically if you want to do abrasive jet machining, the assumptions is the abrasive particles normally assume spherical in shape, then impact also produce some spherical indentation, and equal what is the indentation, it creates the same amount of volume is actually is removed from the surface. These are the typical assumptions if you want to establish the theory for brittle materials. Normal impingement of the abrasive particles is the mechanism for, we assume the abrasive normal impingement of the abrasive particles. Finally, rupture due to the spherical indentation caused by the impact of the abrasive particle is the main mechanism. Rupture is the main mechanism of the material removal using the abrasive jet machining process. Now, if you look into the similar calculation we can perform also in case of abrasive jet machining. If you see that these are the different parameter: indentation depth, diameter, this is the diameter of abrasive particle, and mass flow rate of the abrasive particles. So, similar way what we discussed on the earlier, and ultrasonic machining we can use some kind of particles, and this is the, it creates the diameter diameter of the indentation, and h is the indentation depth, and m is the mass flow rate of the abrasive particles which we control, we can estimate, calculate mass flow rate of the abrasive particles and proportion of the abrasive particles effectively propagating the erosion of the machine. Actually, not all the abrasive particles is actively taking part in the erosive action, rather we can say that we can introduce some efficiency term that indicates, that introduce the what is the effective amount of the abrasive particles is takes parts in this process. Density of the abrasive particles, then n equal to number of abrasive particles striking the work surface. So, n is the number of particles striking the work surface, b is the velocity of the impacting abrasive particle, and flow stress of the workfree material, and the of course, volume of the workfree material removal per impact of the abrasive particle that we have already discussed. That if we look into the volume, we can estimate the volume of this part, then we can find out that it is a half spherical having the diameter d, capital D, and then it estimates the what is the volume of the material removal per impact of the abrasive particle is this amount. So, therefore, number of abrasive particles striking the workpiece surface. So, number of particles striking the workpiece surface that we can estimate in the other way also. So, we know the mass flow rate m a, and what is the this, what is the volume flow rate, volume of the workpiece material impacting per abrasive particles, which is 1 by 2 and here 1 by 6 pi dq, and we can, from here we can estimate the relation d is approximately twice h into d. So, from here we can find out 1 by 12 pi d cube 8 h d 3 by 2. So, here we can find out at h by d by 2, we can find out that 2 by 3 pi h d 3 by 2 can be estimated at the volume, or other way you can see this is the volume in terms of this equivalent to the volume of the work material removal per impact of the abrasive particles. This can be estimated like that 2 by 3 pi h d to the power half. But other way also we can estimate that number of abrasive particles striking of the workpiece. What is the volume of the abrasive particles? We can say volume of the abrasive particles. This is the volume of the abrasive particles, 4 by 3 into by 8. So, 1 by 6 pi dq is the volume of the abrasive particles. What is the mass of the abrasive particles? 1 mass of the abrasive particles is the density of the abrasive particle. So, 1 by 6 pi d cube by rho a is the mass of the one abrasive particle. So, when we divide m dot a divided by this, if you see like this 1 by 6 pi d cube rho a, this indicates the mass of the one single particle. So, then mass flow rate divided by mass of the one single particle, that indicates what is the number of particles is actually striking to the workpiece surface. This we can estimate. So, with these parameters we can find out what is the volumetric material removal rate, that means volume of the V equal to volume of the work material impact per impact of an abrasive particles, and N equal to number of abrasive particles is actually striking on the workpiece surface, and we multiply by this fraction, maybe that indicates what is the effectively actual number of particles is actually participating in the machining process. So, basically N into eta a, that actually indicates the what is the effective number of particles actually participating here during this process. Now, here considering the indentation cost due to the impact, similar spherical indentation it creates a diameter of the workpiece material at any instant time, the similar calculation we have done, d equal to s 2 d. Material removal rate we can estimate that this is the volume of the this thing, it is a capital V, this indicates the n, sorry, and this is the n into, and this is the effective, that indicates the effective value of the particle is actually in impact. So, if we do this, we can get this expression which is represented in all these parameters. So, indentation depth can be evaluated by equating the kinetic energy of the impactive abrasive particles to the work done in the producing the indentation. So, other way also it is possible to find out the indentation depth, because here the kinetic energy for indentation we can say that is the, we know that kinetic energy half of mass into velocity square, which is what is the amount of the work done in other way also. The flow stress, it covered the flow stress value, that area, that force into it impact up to the distance h. So, force into distance, that work done or energy equivalent to that, make this equal flow stress into energy, and then from here this is equal to dH square. So, from here we can relate different way. So, that H can be represented like this, H equal to in terms of the d particle velocity and the this thing. Or finally, material removal rate, if we replace in terms of H, then we can find out the material removal rate. Maybe this constant comes from the here, but it depends on the this way the parametric value of all these parameters, efficiency, mass flow rate, velocity, density of the particle and the flow stress value. So, all this way we can estimate what is the material removal rate in case of abrasive jet machining, but parametric analysis indicates that few significant points, that fine grains are less irregular. So, that is laser cutting ability may be reduced, or stickings to get stuck with the stick together with the workpiece material. That is the one problem in case of fine grain size. So, abrasive flow rate increases, the material removal, definitely abrasive flow rate increases, the material removal rate also increases, and more abrasive becomes available for the cutting action. Metal can also be increases if we increase the gas pressure. So, gas pressure increases when increasing the gas pressure, but the increment of the gas pressure as a decreasing rate of increment should be low, and that tends to saturate beyond a certain value. So, we can increase the gas pressure up to certain extent to increase the material removal rate. So, carrier gas actually attains the maximum velocity at the end of the nozzle exit and start decreasing with the stand up distance. So, stand up distance should be optimum way. To accuracy of the cut depends on the stand up distance, which is increases due to the spreading of the jet. So, stand up distance increases, jet will spread. So, that actually deteriorate to the surface finish probably. The advantage, very hard, heat sensitive and fragile materials can be used in case of abrasive jet machinings, and one of the least expensive non-traditional processes, and shockless cutting action is possible by abrasive jet, which was difficult in case of probably in that water jet machining, no part chatter or vibration. Application, we can find out glass rod, drilling glass, cutting, all these cases we can found the application of the abrasive jet machining. Limitation is that low material removal rate, taper can be produced, but it depends on the shape of the stand up distance, and short nozzle stand up distance used for cutting, and particles can be embedded into the workpiece. So, that is the main difficulty, and it depends on the what is the size and distribution of the particles, and normally fine particles chances of the embedded to the workpiece during this process.